Okay, so in this lecture, I'll talk about dynamic analysis. So on the previous videos, that is all about static analysis. So in dynamic analysis, we will now work on the equation of motion. So the general formula for equation of motion is something like this: mu double dot plus cu dot plus ku equals uh, this could be zero, no, for ano, no, for free vibration, no. This could be equated by mg double dot pag meron kang um, earthquake ground motion. Yan. Or this could be equated by p sine omega t. Yan. If harmonic motion. Yan. So as you will see, yung equation of motion na yan, so equation of motion. So it involves now mass. Yan. Tapos u double dot, yan yung acceleration. Plus c, okay, yung damping. Tapos u dot, the velocity. And then k, stiffness. Itong ku, you should be familiar with this, no? Because yung sa stiffness method, as you have learned sa structural analysis, the general formula of that is actually P equals KU. Yan, no? Wherein yung force mo is equal to stiffness times the displacement. Basically, no? Parang you can idealize your structure something like meron kang spring having a K, no? Tapos say this is your structure, no, or SDOF or single degree of freedom na idealization, or nilamp mo siya, no? Okay? So may stiffness siya, tapos once binigyan mo siya ng vibration or simply force, or itulak mo siya, no, sa statics, no? If you apply a force going there, so magkakaroon siya ng corresponding displacement, which is u. Okay? And that displacement will depend dun sa stiffness of your spring. Okay? So that's the analogy, no? It's a spring it's a spring idealization. Okay? So but in actual, no, in software, no, this K is in matrix form. So malaki yung matrix na yan. But in our lecture sa dynamic analysis, we will just idealize the structure as single degree of freedom. Okay? When we say single degree of freedom, SDOF, from the word single, no? Okay, I can't write. Oops, what's happening? Okay, so when we say SDOF, no? SDOF. So single degree of freedom system. So we idealize the structure as this one, parang lollipop, no? We will lump the mass here. So yung mass of the structure, idealize natin here. Tapos it has corresponding K, stiffness. Okay? So I guess you're familiar with this already, no? Do sa ating mga first video. Yeah. So that's how we got the period, di ba? Wherein period is equal to 2 pi square root of m over k. So it's a function of mass and stiffness to get the period. Okay, so single because the the displacement of this model is 1, or single, no? You can only displace laterally, no, by say during the earthquake, if this is your model, you can displace laterally from left to right. So sa x direction. So single degree of freedom. So degree of freedom means the number of freedom you are allowed to to displace. Yeah. Okay. So first we will talk about the undamped free vibration. So undamped means um, you don't have parameter of damping. Let's assume a structure has no damping, okay? And free vibration, therefore, this is zero, okay? No force is no force is applied, no? So this is crossed out, no? So in the simple equation, the undamped free vibration has an equation like this, okay? So this equation is a second order differential equation. Yeah. Because second order differential equation. And homogeneous because your equation is equated by zero. Okay, homogeneous. And if you review your differential equation, you can assume a solution in this form. So your unknown is the U, okay, because mass and stiffness is given, diba, in your structure. Therefore, your unknown is the U. Okay, so we can assume a solution in this form. U is equal to E raised to ST. All right. Or on the other solution we have here, I have here also. If this is your solution, you can come up with this general equation, this one. Okay. So I want you to show two solution. Let's see. Yeah. Okay. So mu double dot plus ku equals 0. So that means to get the u double dot or the second derivative, you need to first get the first derivative. So get the first derivative of this, of our assumed solution. So u dot is equal to eu du. No? So our derivative is se raised to st. Right? So first derivative of eu is equal to eu du. Right? Get the derivative of u. Our u is st. So du is s. Okay. Then u double dot is simply the same, no? est, and but the du is s again. So s times s is s squared. Okay, then plug in this solution, or sorry, this double derivative in our original equation. So mu double dot is equal to m times s squared est plus ku, which is est, is equal to 0. Then get the common factor. Our common factor will be est. Yan. So we will be extracting the ms squared plus k times e raised to st is equal to 0. Yan. But our solution is est, right? Therefore, est cannot be 0, no? Because that is our assumed solution. Therefore, this equation to be true, the ms squared plus k will be 0. So let's equate ms squared plus k is equal to 0. Okay. Then transpose this. S squared is equal to negative k over m. And then get the square root. No? Because this is negative, I will now introduce the imaginary number, I. So our s is equal to plus or minus I square root of k over m. And take note, omega, or the frequency, this is your frequency, no, is square root of k over m. So if we rewrite this, S is equal to plus or minus I omega. Right? Now let's proceed with another way of solving that. Okay. So again, I rewrite this. Mu double dot plus Ku is equal to 0, wherein the general solution has a form of C1 sine omega t plus C2 cosine omega t. Okay. So if you review your differential equation, you will see this solution. Okay. And then let's find out uh, the u at time equals 0, because remember, our structure is at rest, no? Free vibration, no? It's at rest. Sorry. This is at rest. Therefore, your initial u at time 0 is equal to 0, no? Wherein time is equal to 0, and your velocity at time is equal to 0 is also 0, because it's at rest, no? So at rest, initial condition. Okay. So plug in. So u at time is equal to 0. So C1 sine omega times 0. So that is omega times t equals to 0. So sine 0. Plus C2 cosine omega times 0. Okay, so that will be cosine 0. So cosine 0 is simply 1, right? And sine 0 is 0. Therefore, u naught, or initial u, is equal to C2 times 1, because this is 0. This is 0. Okay? So what remains is u0, or u naught, is equal to C2 times 1, and therefore C2 is equal to u naught. Okay? Then, as we did here earlier, get the first derivative. U dot is equal to first derivative of this one, no? Derivative of sine is cosine, right? And cosine u du, no? So du is omega, okay? Because the general equation is a function of time, no? So our variable is omega, okay? So sine omega t is w omega cosine omega t times c1. Derivative of cosine is negative sine. Okay, so that's negative sine omega sine omega t. Then, with the initial condition of u dot, or initial velocity, is 0, so plug in here at time 0. U dot is equal to c1 times omega cosine times omega t. Sorry, time is 0, so this will be cosine 0, right? This will be 0. While this one will be, this, because sine 0 is 0, so this will be crossed out. This is already 0. And this whole will be 1. Okay? So C1 times omega times 1, this one above, minus C2 times omega times 0. And again, this is crossed out because that is 0. So u dot is equal to C1 omega. Okay. Zoom in ko siya. Okay. So it turns out our C1 is this. Oops. Sorry. This one. So that is our C1. Since we now know C1 and C2, plug this into our original equation. Okay. So U is equal to C1 sine omega t. Our C1 is U dot over omega. So U dot over omega sine omega t plus C2 cosine omega t. C2 is U naught, so U naught cosine omega t. So this is our solution. Okay. So the general equation of the solution of this differential equation is this. Okay. So if you plot this in a spreadsheet or in Excel, you should come up with this kind of graph. So wherein this is your U, and this is your x-axis or your abscissa is in time. And the distance between this one up to this one is what we call the period, which is 2 pi over omega, because frequency is equal to omega over 2 pi. That's why since omega is remember, omega is the square root of k over m, right? So therefore our period is equal to 2 pi square root of m over k, right? Now, since this is free vibration and undamped, if you plot this here, this one, this is this will be continuous, no? It will not this motion, the amplitude of motion will be infinite, no? Because you have no damping, no, to damp out the motion, no? So that's why you will come up with this kind of graph. It's continuous, no? So imagine your structure is this, no? Tapos you don't have any damping, no? Wala kang damping sa structure. So if nag-vibrate yan, so infinite yan, no? Hindi matatapos, no? Kasi wala kang damping. That's the physical meaning of that, no? And yung amplitude ng motion mo, nung mga U mo, U displacement, pag plinat nyo, you will come up with this. Okay? Now let's relate if you have a rigid structure. If you have a very rigid structure wherein yung K mo, so pag rigid, no, your K is going infinite, no? So if this is infinite, what will be your period? So sobrang laki nung K mo, no? Tapos yung ma-overpower nyo yung mass. Therefore, your period will be approaching zero, no? Sobrang no? Sobrang stiff ng structure mo such that rigid ka. Your period will approaches zero. Whereas if you have a very flexible structure, no? Very flexible structure, kabaliktaran naman, no? Your period will approach infinity, no? Sobrang flexible mo. Okay? So that is the solution for the undamped free vibration. Now, what if, no, you now have, let's introduce the damping. Meron kang damping sa yung structure, which is the more realistic one, no? Meron say for a building, meron tayong damping, no? Kaya nga say pag nag-vibrate ka during earthquake, hihinto yan, no? Kaya humihinto because you have damping. So now your equation of motion is now this: mu double dot plus cu dot plus ku is equal to 0. Okay?